Right, hi, welcome to your third lab. This is the Bernoulli lab. So this is coursework 3 out of 4. Just a reminder, your final coursework is a group presentation. So Bernoulli, you recognize the Bernoulli equation here at the top. We'll come back to that shortly. Let's have a think about what happens, how we demonstrate the Bernoulli effect using a piece of equipment called a Venturi meter. So this is the Venturi meter. This is a little sketch, a 2-dimensional sketch. And what you would use a Venturi for is to calculate the discharge at any point in your pipe system. So here's your pipe system going along like this. And then you would attach a Venturi meter, which is very simple. It's just a reduction in the pipe diameter to a smaller diameter and then a gentle return to the original diameter. So Bernoulli is using the continuity equation to calculate what the flow velocity is in this pipe. So let's have a think about what happens to our little flow vectors as they travel through our pipe. So again, these are vectors, so it's given us a magnitude and a direction. So the size of these arrows is important. So our flow is happily pootling along until it reaches this point where suddenly the area, or in this case the diameter of the pipe, is starting to reduce. So the flow needs to speed up in order to retain continuity. So Q equals U times A. That area is getting smaller, that U value, that velocity must increase for it all to equal discharge Q. So let's start drawing a bit of a larger arrow. I've drawn it near the boundary. I'm not entirely sure why. I should have done it in the middle. Once we get to our smallest diameter, our flow velocity becomes the fastest. Okay? But then as you get out into the return of to the original pipe diameter, our flow vectors are starting to get smaller again until they become approximately the same size as they were originally. Okay? So, to recap, flow is, through this pipe, is its normal value. The vectors are sort of a small size, but they then increase when the Venturi throat starts to decrease the diameter of the pipe to a maximum, and then they return to the original flow. So, using Q equals U times A in the Bernoulli equation, you can tell what the flow velocity is by looking at the difference between the vector size here and the vectors here, and knowing about the diameter of the pipe. However, in real life, it doesn't quite happen like that. Because in this case, we're assuming that there is that this is an inviscid fluid, okay? It's an ideal fluid. It doesn't have a viscosity. But of course, we know if it has a viscosity, it must then interact with the boundary layers that are generated in this pipe, which we'll have talked about quite a bit in the lectures. And so, namely, friction produces losses. As it comes into this point, you'll start getting turbulence, separations. As soon as you have turbulent flow, you're starting to bleed energy out. It generates noise, it generates heat, and therefore you get a loss in energy, Bernoulli being the energy balance, and then these vectors, the flow velocity will be slower at this point. So, very briefly on this, I'll just talk about Bernoulli's equation to remind us all before we look at the actual experiment itself. You've got the pressure head. Remember, there are 3 different types of energy in a flow. There's the pressure head, the velocity head, and the elevation head. Now, in this experiment, we can cross out our elevation heads because we have a horizontal Venturi meter. Now, with a bit of rearrangement, we can come up with this equation, which tells us in our Venturi meter, one thing I haven't mentioned, the way we would measure our pressure head is we'd use manometers, which we'll have talked about in the lecture, which is giving us a value of the pressure head at any point. So at this point, it'll be a bit lower because the velocity head's increased. At this point, our pressure head will be the lowest because the velocity head is the highest. And we're looking at an interchange between the two because we've cancelled out the elevation head. And then we'd have thought, if the fluid was an ideal fluid, that this pressure head here would be the same height as this one, but in real life, it's not. Therefore, it's showing that we've lost a bit of that energy. So with a little bit of rearrangement, we can show, and we'll go through the rearrangement in the lectures, we can show that the height of the manometer at the second point, or the nth point, must be equal to the height at the first point minus the change in velocity head. Now you'll find that when you use this for the data, you should find that it doesn't match up with the theory, and that's the whole point of this lab. Anyway, without further ado, we'll move on to the actual demonstration. Right, welcome to coursework 3, the Bernoulli experiment. This is your third and final lab experiment. So what we have here is the setup, which is the Venturi meter down here in the Perspex box, an array of manometers, and a tube that cycles the constant discharge through the system. And inside here, there's a pump doing all that work. So let's remind ourselves about the Venturi meter, what it looks like and what it does. Effectively, at the start here, we have the inlet, which is the same diameter as the pipe. And then it has a sharp decrease in diameter to the throat of the Venturi, and then it slowly, gently increases back in diameter to the original diameter of the pipe. Venturis are used to calculate the discharge in a pipe system. Very useful because there's no moving objects. There's no propeller inside here and digital counter to count that. You know, you could lose the voltage or the propeller could break. In this case, not a lot can break. We're going to use it to demonstrate the Bernoulli effect. And to do that, we can use these manometers. So a manometer is simply a tube that measures pressure. Now, if you remind yourself, the Bernoulli equation is pressure head add velocity head add elevation head at point 1 is equal to pressure, velocity, and elevation head at the nth point, any other point, for an ideal fluid. In this setup, we can cancel out elevation head because the Venturi is a horizontal Venturi. Okay? If it wasn't, or in some of your pipe systems it's not going to be, so you have to include elevation head in your calculation. Here we can cancel it out, and all we can then say is the pressure head and the velocity head at point 1 must equal the pressure head and velocity head at point whatever, the nth point, or this point here, where it returns the original diameter. That's the theory, but if you look at actually what's happening, what it should read out as is a pressure head at this point being the same as a pressure head at that point, but it's not. There's a difference of about that much. So what's going on? The water's coming into this diameter here, it's accelerating quite quickly, which is why the pressure head drops, but the velocity head is increased as a result, and then it decelerates back to the original diameter, so the pressure head should be the same, but it's not. Why is that? Because it's a real fluid. It has a viscosity, and therefore it's going to have boundary layer interactions, friction is going to play a part, it's going to generate turbulence, especially when it gets into this middle throat, and there's going to be losses through that. Turbulence generates sound, which is a loss, and heat, which is a loss, for example, and eddies are generated. So in the real life, you have a head loss, and it's important head loss, because if you're designing a pipe system, it is an important parameter that you have to account for in the size of pump you have, or the level of discharge you want. So in your coursework, you'll be given a data sheet with 3 different discharges, so 3 different settings on this valve, and the manometric heights in meters of the piezometric height along this Venturi meter. So at this discharge, which is the highest discharge, we have this picture, but if I was to close the valve slightly, in effect lower the discharge, just have an observation of what happens to the pressure heads along these manometers. And in particular, focus on this one, and this one. So reducing the flow rate, we're reducing the velocity through the Venturi. And because the velocity is lower, the acceleration is lower, and we have a higher pressure head in the throat. And also, importantly, the difference, the head loss between the entrance and the exit of the Venturi is much smaller. It's only about that much now. So again, an important thing to consider in pipe engineering. Can you find the sweet spot in the amount of discharge you want, and the size of pump that you can afford, and the amount of head loss that you're going to generate? You also might have noticed that the fluctuations are slightly less. So if we reduce the discharge one more time, again watching those manometers, I think I can convince you the head loss between here and here is only about 1 centimetre, so it's much less. Now you could reduce this completely to a very low flow, so it would be a laminar flow, and the head loss would be very, very small. If it was truly laminar, it should be 0, but I'm not going to get that in the physical world really very easily, certainly not with a piece of equipment like this.